All right, so since we're looking at if this reaction is thermodynamically favored, we have to use the equation for Gibbs free energy, okay? And so what we're going to be doing is plugging in as much information as we can into this equation in order to figure out if it's going to be spontaneous or not. And I gave you guys this table to kind of help you guys with that. Okay, so we can take a look at enthalpy, to change enthalpy first. Is this going to be a positive or negative number? Negative, yeah. Enthalpy is negative because it's negative 46 kilojoules per mole. So this is going to be a negative number. All right, and then we're going to be subtracting. We don't know the temperature, so we can leave the temperature like this. And then we're going to take a look at the delta S, okay? So delta S, we talked about how this is entropy. And what's another way that we can define entropy? What does entropy mean? Yeah, random. So basically randomness, okay? So entropy measures randomness. So basically here, the delta S, we're trying to figure out, is the system becoming more random or less random, okay? Now, if you guys take a look at this, all three of the compounds involved are gases, right? And so what we want to do is take a look at how many moles of gas we start with and how many moles of gas we end with. So in the reactant side, how many moles of gas do we start with? 4. We start with 4 moles of gas. Okay, but on the product side, how many moles of gas do we have? 2. Okay, so just thinking logically, if we go from 4 moles of gas to 2 moles, is the system getting more random or less random? Less random, right? Because there's more consistency in how the molecules are going to move. So that means that for the delta S, since it is getting less random, is it going to be a positive or negative number? Yeah, so it's getting less random. So let's think about this. So 2, so remember, it's always final minus initial. Okay, so the final is 2 minus 4. So is it going to be a positive or negative number? Negative, yeah. So that's one quick way you guys can, figure out if it's positive or negative. I know it's a little bit trickier, right, to think about randomness is going to be positive or negative. But just remember, the delta equation is always going to be final minus initial, no matter what you're talking about. So the final is 2 moles minus 4 moles. So it's going to be -2. So it's going to be a negative number. Okay. All right. So far, so good. All right. Okay. So now we can take a look at this equation. Now, actually, we can start plugging. We can put in the numbers. So we just put in the negative signs for now, but it looks like for this problem, we're going to have to figure out what the temperature is as well. Okay. So let's plug in our values. So we're going to plug in for enthalpy -46 minus T. And then this is going to be -2. You okay? You're going to break your other foot. Okay. So based on this information, we can start deriving some things out of this. Okay. Now, depending on what T is, this G can be positive or negative, right? Okay. So if we take a look at T right here, okay, if we increase the value of T, if T is bigger, okay, so let's say we make T a big number, like let's say it's 1,000, right? If T is 1,000, is G gonna end up negative or positive? It's gonna be positive because if you take a look at T, so let's plug in 1,000 for T, or let's do 100. We can just do it with 100. Okay, so -2. This is going to end up becoming -200. -46 minus -200 is positive. So -46 plus 200 means that we'll have a positive delta G. You guys see that? Okay, so if G is really, really big, that means that, or sorry, if temperature is really, really high, that means that the delta G is positive, okay? However, let's say that the temperature is really, really low. Obviously, it's going to go the other way, right? So you'll get a negative delta G. Okay. All right, so based on that info, we can already tell that A and B are incorrect, right? It's not always or never. It depends on the temperature. Now, which temperature is the reaction going to be spontaneous? High temperature or low temperature? Low, yeah, because the lower the temperature, you want delta G to be negative. I know it's kind of weird. Negative delta G means that it is spontaneous, but low temperature is when this reaction is going to be favored. Okay, so your answer is going to be C. So I kind of went through that slowly because I know the positives and negatives and the numbers, it can get really confusing. There's too many of these signs, but when in doubt, just use this equation to slowly work through the problem and you should be able to figure out what it is, okay? Okay, because if you look at this, this is a pretty simple math equation, right? It's just basic algebra, okay? All right, any questions? Okay, I'm going to give you guys a couple minutes. I'll leave this up here for a second, but if you have your problem up on CAT, actually, not a lot of you guys don't. Let's move on. Okay, I'm going to give you guys a few minutes to try 13.10, and then after that, we'll go over it. Pretty simple. Okay, so all we got to do is take our starting value of 64 grams of our compound, and then we want to figure out how much energy is released or absorbed. Super simple. So we just take the molar mass of the compound. Should have gotten 32 grams for 1 mole. Okay, and then you're going to multiply, because every mole, this is a balanced equation, obviously, it's going to release 65 kilojoules. And so you should get negative 130 kilojoules. Okay, and since it's negative, it's going to be released. So it'll be D. Yeah, woohoo!
How many of those types of problems will be on it?
Not too many. I wish. Yeah. And it's like integrated with other stuff. You'll see the old, I'll show you guys the old FRQs soon. But yeah, they're not fun. And you guys have seen some of the old FRQs. I put them in your tests already. So fun. All right, let's move on to 13.11. I'll give you guys a few minutes to look at 13.11, maybe 2-3 minutes, and then see if you can get an answer. All right, so we got a 2-liter flask that has some helium gas in it. So let's say this is a flask, 2 liters. You got 0.4 grams of helium in there. And then it is moved to another container, a larger container. Okay, and the temperature is held constant. So if we move the helium gas to the other container, you still have the same mass of helium gas, okay? Now, we're trying to figure out the effect on the entropy or the randomness, okay, on the helium gas, okay? So hopefully you knew that it's not going to remain constant, right? Because if you move a gas to another container, obviously it's going to be more, or it's going to change somewhat. It's going to be either more or less, okay? B does not make sense because if you move something to a larger flask, it's not going to be more ordered, right? Okay. C and D are probably the only ones that really make sense, okay? But if you take a look at C, it is true that the molecules will collide with the size of the flask less. However, because there is more volume and more space, okay, the gas molecules will be more spread out. And because they're more spread out, the actual entropy is going to increase. Okay, so the answer will be D. So C does kind of make more sense than the other ones. However, C doesn't take into account things like bumping into other gas molecules, right? It doesn't take into account the fact that it's more spread out. And we know that the more spread out something is, the more random it's going to be, right? So the answer will be D. Okay, but if you put C or D, you're on the right track. Yeah. All righty, let's move on. Dang, there's a lot of questions. Jeez Louise. Okay, I'm going to give you guys 30 seconds to try this one. This one should be pretty quick. Okay, you got liquid water turning into solid water or ice. I want you guys, based on that reaction, okay, liquid water to ice. Okay, which of these are true? Okay, maybe more than 30 seconds. I'll give you a minute. Okay, so we got water going to ice. So let's take a look at option A. So if you take a look at option A, delta S is positive. Okay, delta S is entropy. So if it is becoming positive, if delta S is positive, does it become more random or less random? Yeah, more random. Okay, and again, if that is kind of confusing for you, just remember delta anything is final minus initial. Okay, so if this value is positive, that means the final has to be bigger than the initial, right? So that means if it is bigger, and then we'll do less. Sorry, I forgot the answer. Okay, bigger. Since the final is bigger, that means it's becoming more random. Okay, all right. Delta G is 0. Okay, if delta G is 0, that means that this reaction is neither spontaneous or non-spontaneous, right? It's an equilibrium. Okay. Okay, now this is a viable option, right? But then the thing is we don't have any information about the temperature or the pressure or anything like that. So this is like sometimes. So let's kind of put a pin on it. Let's not cross that out yet. Oh, sorry, I didn't mention this. A is obviously wrong because if you go from a liquid to a solid, it's less random, right? Because it's not moving as much. Sorry about that. So let's put a pin on this one for now because sometimes it's true. If we go to C, delta H is positive. If it is positive, does that mean it is exo or endothermic? Endo, which means that it is absorbing energy, right? Okay, now if we think about it, when something freezes, is it absorbing energy? No, because if it's absorbing energy, it would get hotter, and ice is not hotter than water. So this is obviously untrue. And then lastly, D, it's favored at 1 atm, 298 Kelvin. And if you guys do the math for this, this is 275. I subtract 275, sorry. 25 degrees Celsius. Okay, but if you also remember, this is gonna be, do you guys remember the term for this?
Standard.
Yes, STP. Yes. Wow. And yeah, that's gonna be your name. It's D. It's gonna be D. Oh, I'm so sorry. I'm stupid. That's wrong. My bad. It's 25 degrees Celsius. Guys, I'm sorry. I'm not myself. It's B. Sorry. I apologize. B. Delta B is 0. I know. Ian, do you want this come up? I'll get off. I'm done. Yes.
But if it's why is it?
So we didn't know because there's no information about the temperature or anything like that. And so we've kind of just put a pin on this for now. And then since all three of them didn't work, B is going to be your best answer. Yeah. Yes. That's a good question. No, this still works. Because it's still one direction of the equation. Yeah. Sorry. I totally read this as 0 for some reason in my brain. Yeah. Alrighty, let's move on. We're gonna go on to the last problem, and this is gonna be a super big FRQ. Okay. So yeah, I want to show you guys how we can incorporate a lot of different things into the same problem, which is very fun. All right. So we have this chemical equation, and what we are going to be doing is we're going to ignore the enthalpy part for now. Okay, but we're going to be finding the entropy value, so the S value for the overall reaction. Okay, so we're going to be looking at these things right here. Oops. This right here. Okay, so based on this information, we're going to be figuring out the change in entropy, the delta S, for this equation right here. So I'm going to get you guys started with the equation, and then I'll have you guys finish it up on your own. But the delta S is, like we've been talking about, it's going to be the final minus the initial. Okay? So you have the entropy values for each of the compounds in your reaction. And what I want you guys to do is I want you guys to just calculate what your delta S is going to be. Okay? So take a couple of minutes to do that, and then we'll go over it together. All right, guys. So if you guys take a look at A, right here, Elizabeth. Okay, if you take a look at the enthalpy values again, or entropy values, it's going to be final minus initial. So you got all of the compounds, so you can just multiply it based on the mole ratio, and then subtract the reactants from the products. And so you should get a final delta S of 289 joules per mole kilogram. Kelvin. Yes.
I have a question.
Yes.
So before on the last problem we did the entropy or whatever. And it was moles minus moles minus.
Yes.
Why are we doing this?
Because that one we were just seeing the general, yeah. Okay. This is the more specific, yeah, because you're getting the actual values. Yeah, use the values if they're given to you. Yeah. Yeah, that one also we were just taking a look at yeah, just taking a look at the mole. So the values would be different. Yes, but it's the randomness for energy. Because if the more random something is, the less energy it has. And so yeah, remember that what is it? The phrase that we looked at? Nature wants to go towards high disorder and low energy. Yeah, and so that's how it relates. Yeah. Okay. Good question. Yeah. Oh, these units of measurement right here. Mole time Kelvin. Sorry, there's I wrote Mo. Mo Kev. Yes. So higher energy means more like for each one right here, like 220, that'd be the most random subsets. Technically, would that be the least? This is just telling you that randomness is increasing. Okay. Yeah. Okay. Alrighty, let's move on to enthalpy now. Now, you're gonna need this table. So if you guys don't have it up, try to share with the person next to you. If not, take a picture of it real quick because I'm gonna cover it up. But we're going to be taking a look at the enthalpy value of the overall reaction. Now, in order to do this, it gets a little bit more annoying because if you take a look at it, we don't have the enthalpy values for each compound or for the overall reaction. Instead, you get a table with the bond energies. Okay, so this is very annoying. What you have to do is you need to figure out the structure of each individual molecule and then figure out what bonds there are, and then use the table in order to figure it out. So the first thing that you want to do, let me go through the structures with you guys just to kind of speed you through it. Yeah. So you're gonna have to, you'll see in a second. Yeah. So first you're gonna want to draw the structure for all these. So I'm gonna do them for you, just to kind of speed through this process. Okay. So we got NH3, and NH3 looks like this. Okay, but if this was actually on your test, you would have to draw all these. Okay, or if you can mentally see it and then do the math, then that works too, I guess. Okay, N2O is going to look like this. Not O. Okay, and then it's going to produce N2, which is triple bond. And then H2O, this one you guys are probably familiar with. Looks like that. Okay. So that's what the structures look like. Now, I'll give you guys some time to draw it and then go over, try out the problem on your own. But if you notice, you can see all the bonds that are there, right? Okay, so each compound has different bonds in them. And what you're going to want to do is you're going to want to refer back to the table, and that table tells you the energy that each bond has. Okay, and then the same thing here. What you're going to do is you're going to do delta H, and it's going to be the sum of all the products, okay, minus the sum of all the reactants. Okay, and just keep in mind, this is my little hint for you guys, keep in mind the mole ratios. Okay, because that's gonna affect how many of each bond is actually broken and produced. Okay, so this does get a little bit annoying, just because of all the things that are going on. Okay, so I'm going to give you guys maybe about 3 to 4 minutes to do this one, and then we'll take a quick break, and then we'll finish up this FRQ and hopefully start unit 14 today. Alrighty, guys. So I did make a small error as I was going through this. Nothing with the struct. What the freak? Nothing with the structures. All right. Anyway, it's not the structures that I made a mistake with. It was the equation. I totally forgot a little nuance with the delta H. So one quick thing about the delta H equation is that you can't just do the products minus the reactants, because what we're looking at here is the bonds being broken and the bonds being formed. Okay, so the total amount of energy that you start with is going to be the bonds broken. Okay, so basically the amount of energy that's broken, and then depending on how much energy is released, right, we're going to subtract the bonds formed from there. Okay, and so this is what's going to allow us to figure out the change in energy. Okay, because the starting amount that you had was the energy that's within these bonds that are broken. Sorry about that, guys. So if you guys did it incorrectly, all you need to do is flip the sign, and that'll give you the correct answer. Okay, and then the energy used to form them. Okay, so let me just briefly go through it. So I don't have the structures up here, but you can double check with your pictures. Okay, but you should calculate that there were 6 NH bonds. Okay, and then there were also 6 N-double-O bonds. Okay, everybody good with that? And then all you're gonna do is subtract 4 N triple bonds. Okay, plus 6 OH bonds, the best bonds. Okay, and then all you had to do was plug in the values from the chart, and you should get a total value for the energy broken, the energy in the bonds broken, 6108, formed 6542. Okay, and so you're going to get a total of negative 434 kilojoules per mole. If you got positive, that's on me, so you did it correctly because I gave you the wrong equation. I apologize, but 434 should be your correct answer. Okay? Great job, Brendan. I'm so proud of you.
Yeah, you know what? Don't inflate his ego. It's gonna.
Dude, I need to inflate his ego. Brendan, you are amazing. You are beautiful. You are tall. You are. He's 9'9".
Wow.
You can jump over a car. You can run into traffic and you won't get hurt. Yeah, you probably get flipped over. You can fly, Brendan. Yeah. Yeah. Maidens weep when they see you out of awe. All right. Anyway, let's move on. All right. So do you guys all have the delta S and the delta H value written down somewhere? Okay. Okay. So this is the delta H value. And then a quick reminder that your delta S value, if you guys didn't write it down, was 289 joules per mole Kelvin. And this was the answer from part A. Okay. All right. So make sure you guys have A and B written down because we're going to go to part C. And for part C, all you're doing is you're going to calculate if the reaction is thermodynamically favored at 25 degrees Celsius.
Oh, you can still do it even though S is equals and the other one is equal to.
So you'll have to convert.
Okay.
Yeah.
S.
Either whatever you like. Okay, so let's go to part C. What I want you guys to do now is based on the information that we have, I want you guys to calculate, and that's the justification, your calculation, if this reaction is thermodynamically favored at 25 degrees Celsius. And the way that you can do that, very simple. Delta G is delta H minus T, delta S. You're going to plug and chug. Just remember to make sure all of your units of measurement cancel out, okay? So take a minute to do that. And then we're going to skip part D, so don't worry about that. You guys don't need to start it. Yay. Okay, guys, so we're just going to plug in the values that we had. The key thing is we need to convert entropy and enthalpy into the same unit of measurements. Just make sure you guys did that. I'm going to make them both kJ. So just keep that in mind. If you did it both J, that's fine as well. But for delta H, you should get negative 434 kilojoules per mole. Okay, minus, and then since it's 25 degrees Celsius, make sure you convert it to Kelvin. Okay, and then it's going to be 0.289 kilojoules per mole Kelvin. Okay, And if we do that, what that allows us to do is cancel out the Kelvin. And then we can just solve from there. You plug into your calculator and you should get negative 520 kilojoules per mole. Okay, and that is your delta G. Yes. Yeah, I believe our delta S was 289 joules per mole Kelvin. Okay, and so since this is joules, in order to add or subtract these two values together, you got to make sure they have the same because it's kJ, right? So yeah, all I did was turn it into kJ by moving it 3 times to the left. You could have done the same thing with kilojoules, but then you would have 434,000 joules per mole. Either works. It didn't specify what to give your answer in, so as long as you have them both in kilojoules or joules, that's totally fine.
Why did you cross out?
What?
Why did you cross out?
Because you're adding and subtracting them, the units of measurement stay.
Oh, because this one multiplies.
Yes, that's correct. Okay. Yeah. All right, so let's take a look at this. It's negative 520. So is this thermodynamically favored?
Yes.
Yes.
Okay.
Yes, it is thermodynamically favored. Yes. Okay, I totally forgot that I said we'll take our break. So we'll take our break and then we'll come back and finish this up. Okay, guys, so let's take a look at this equation. So let's say that 25 grams of ammonia and 25 grams of nitrogen, N2O, sorry, dinitrogen oxide. I totally blanked on the name. We're gonna figure out if energy is released or absorbed. Now, we don't need to do any math right now because we already know the delta H. What's the delta H? That's negative. So is energy released or absorbed?
Released.
Yes, released. Okay. All right, and then so if you guys note, earlier we said that the delta H is negative 434 kilojoules per mole. And so now I'm going to have you guys calculate the magnitude of the energy change. Okay, so how much energy was released? Okay. You start, or the two reactant values we have is 25 grams of NH3 and 25 grams of N2O. Okay, so we're actually going way back. Yeah, stoichiometry. It's from a long time ago. I don't even know what unit it was. We did. I apologize. Brendan insisted.
I did not.
He wanted to exclude you ladies.
Yes.
He wanted to exclude specifically you two ladies. I tried to stop, but he threatened me. It is being recorded. Help. Brendan threatened me to start the lecture without Vivian and Bailey, and now we started without them, and they feel excluded. I was under duress.
You were under duress.
I was under duress. Brendan threatened me at the point of death. I feared for my life if I didn't start this lecture.
What in this class exactly? I don't understand.
Your bare hands. Your bare hands.
Without
Yeah, they're registered weapons. Anyway, calculate the magnitude of the energy change. This.
We're done there.
Yeah. Okay, so let's go into the magnitude of the energy change. So I heard a lot of good things. I heard that people said that this is a limiting reagent problem, which is correct. I also heard somebody say that this is a limited Asian problem, which is also true. I think there are a limited amount of Asians that could do this. Okay, so maybe this one, but you can also write that I have this laxative. Okay, so that's another way that you can, I guess, get points for that by saying it's limited Asian. Anyway. Okay, let's go into this. So what you guys should be able to figure out, there's a lot of different ways that you can figure out the limiting reagent. The way that I do it is I just do the stoichiometry. Whatever gives me the smaller number is the limiting reagent, okay? So I'm not going to do both the stoichiometries just because I want to save time for myself. But the limiting reagent is N2O. Okay. Yes, I'll do. I'll do both of them, I guess, if I really have to. Okay, so you're gonna turn the grams into moles, okay? And then you're gonna set up the mole ratio, so it should be 3 moles. And then we're gonna be looking at either the moles of the reaction or the kilojoules. So negative 434 kilojoules. That's gonna give us a total of negative 82.16 kilojoules.
Sure. Oh, I have a question.
Yes.
So is it just the limiting reagent that you can define for the, like you don't need to add all the moles in the problem, just the moles of the limiting? Why?
Well, I mean, you gotta find it for both of them in order to find the limiting reagent. You can't find the limiting reagent without looking at the moles required for the reaction. Right?
The limiting reagent without, and then like add the amount of moles with like the mole ratio, like find out how many moles of NH3 we use. And add them. Yeah, because isn't it like
if you have a different way of finding limiting reagent and it works, that's fine.
That's not. I'm like thinking about how to get the magnitude because what I did is I got like the amount of moles.
Yeah.
And I did the whole like Gibbs reagent, and then I found the mole of N2O, and then I did the mole ratio from that number. I did like 2/3 to get the mole limit of NH3 that we're used.
Yes.
And then I added them. Good. You don't even do that?
No, because then no.
So it's just the.
Are you still gonna get 82.16?
No.
Then yeah, no. Then no. I don't know what you did, but because that's a good question. Yeah. It's because you're reacting these two compounds, right? Mm-hmm. And it's just the limiting because you're using both of them in order to produce energy, right? Yeah. And as you're using both of them, you're using some of this, you're using some of that, but you end up running out of this. And that's where the reaction stops because you don't have one of the ingredients anymore. And so you just need to figure out how much energy this can make because that's already assuming that you're using NH3 in order to produce that energy. So the NH3 being used is assumed in the reaction, in the calculation. Because you can't make energy with just this or just this. You need to combine them together.
I don't know. I thought of what the amount of more NH3 that was used. Mm-hmm. That's not like
no.
Okay.
Yeah.
That's fine.
Because in order to make this even happen, you're using both of these. I know we're only talking about N2O.
Yeah.
But that's under the assumption that we're using this as well. So yeah, that's not gonna work. Yeah. What's up?
I was gonna ask, like, on that AP test, does it matter how you get the answer as long as it's like correct?
Yeah, as long as it's
like, even if it's like it's not the wood, like if you like go through your process.
Yeah. There's multiple ways to find limiting reagent. I know Mr. Pepic teaches a little bit differently. Yeah, and so if that's a method that you use but you get the same answer, then that's totally fine. Like, yeah. Yeah, as long as your calculations are consistent in the system we're talking about.
Backwards, like.
Yeah. Either way, it's fine. Mm-hmm. And then for the one person that needs the other one, it's going to be NH3, 17 grams. And then you got 2 moles of NH3. And then same thing, negative 434 kilojoules. And then you'll get negative 318.4 kilojoules. Okay, now, there is one thing I do want to mention. So there is one thing I do want to mention because some people do get confused about this. Now, if you're just talking about purely in terms of numbers, which number is smaller if we're just talking about numbers? Yeah, technically this is a smaller number, right? However, the negative sign here is only telling us whether the energy is being released or absorbed. So it's telling us what's happening to the energy. It's not talking about the magnitude of the energy. And that's why even though this is technically a smaller number, the magnitude of energy that's being released or absorbed is smaller here. So that's why this is still the limiting reagent. Yeah, that's one way to think about it. Just make sure you add it back so you know whether it's being absorbed or released. Okay. So the magnitude would be 82.16 kilojoules of energy released. That's what the negative sign means. Okay. All right.
So you just ignore the negative sign entirely.
No, it tells you what's happening to the energy, but the numbers are telling you how much energy, and then the negative positive tells you what's happening to it. Yes. The magnitude tells you the limiting reagent. Exactly. Yeah, that's correct.
Are we graphing?
Yes, we are graphing.
Oh.
All right, let's move on to the graphing. Any questions on this, by the way, before we move on? That's good. Yeah, so make sure you're comfortable with limiting reagents. You're not going to get too many problems. Like, you're not going to have to do this a bunch of times on the AP test, but they might include it, and just make sure you're comfortable finding it, okay? Whatever method you like to use. All right, last one. On the graph, we're going to draw the line showing the progression of this reaction. So basically, how does the energy change throughout? So we're going to draw a graph, and we're going to be plotting the energy versus the progress. So usually the progress is like time, and so we like to put time on the x-axis, okay? And then here, we're going to put the potential energy, so the kilojoules per mole. Now, a couple things. I'm gonna let you guys try this, but I want to remind you of a couple things. We said that delta H is negative, okay? So just make sure you guys keep that in mind. That'll determine your starting and ending points for the graph. Okay, and just make sure you guys label on the graph delta H and the activation energy. Okay, I'll give you guys a minute or so to do it. Just make a general activation energy. You actually don't know the exact value, so that's why it's not asking you for exact numbers. But just generally label what activation energy will look like. Okay, so enthalpy is negative, so this is going to release or absorb energy. Release. What that means is you're going to have a higher starting point than an ending point. So that would be one of the key points on this problem. Okay, we know that there's an activation energy. Now, we don't know how high it is, but as long as you have a bump going up, you're fine. That's activation energy. All right, now we got to label the enthalpy and activation energy on the graph. Now, the change in enthalpy is going to be the distance between the starting and the ending line. So this right here will be delta H. And then activation energy is just the height of this little bump that we need to overcome in order to proceed with the reaction. So there you go, just something like that. Yeah, there are definitely graphing problems on the previous FRQs we'll be doing during the review, so you'll see a lot of graphs on the review, don't worry. All right, guys, congrats. That's unit 13. Okay, we're gonna actually jump right into unit 14 just a little bit, and then I'm gonna let you guys go, okay? Yeah, no, don't worry. It's very quick, okay? Very, 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 very quick. Okay, so unit 14, and you guys do not need to pull it up on Canvas. I'm just gonna go over a couple things. It'll be really brief. We actually touched upon it this unit. Okay, but if we take a look at unit 14, I want you guys to just review on your own or just be familiar with redox. We talked about how oil rig, right? Oxidation is loss, reduction is gain. And just make sure that you're comfortable with working with oxidation numbers. So you might need to spend some time reviewing it. And then just make sure that you're able to do things like this, 14.1 and 14.2. Figure out what the oxidation state is for all of these. We'll go over this when we come back to class. And then figure out which one is oxidized and reduced.